Okay, I think it's time that we start. Hello, everyone. Welcome to this week's seminar. And this week's speaker is Martin Schneebeli. Martin is the head of the research unit Snow and Permafrost at the Institute for Snow and Avalanche Research in Davos in Switzerland. And he's also a co-PI for the MOSAiC expedition measuring snow properties as part of the ICE team. And today, Martin will give us some insights into the expedition and some of the results. So with that, I would say welcome everybody, and over to you, Martin.
Thank you, Rebecca, for the introduction. And today I speak about seeing snow on sea ice during the MOSAiC expedition. As you see from the first slide, there are many contributions. It's really collaborative work, and there are many more contributing to the entire expedition. It's really quite a huge project, as you will see. And my pointer is a bit slow. So the MOSAiC expedition is an acronym for Multidisciplinary Drifting Observatory for the Study of Arctic Climate. And I think the long title really is a quite good expression for the complex operation of this expedition. The expedition started in September 2019 and ended mid-October 2020. And from the picture here, you see it started in Tromsø, went then up about 85 degrees north, where the expedition as such really started on the 4th of October 2019. And then in these different colors, you see the different legs. So between, and these legs were initially planned that after each leg, there is an exchange of the scientists and part of the crew. So the first exchange was mid-December, and then the second exchange was beginning of March. And then there was no exchange between and then leg 3 was much longer than planned. And leg 4 was then from June to August, and leg 5 from mid-August to beginning of October. And you see that the drift distances are very different. So leg 1 drifted very little, leg 2 also very little. Leg 2 actually came quite close to the North Pole. And then leg 3 was very fast going south. And leg 4 was then going close to the edge of the sea ice. And leg 5 then had to go back close to the North Pole and started a bit later, where the possible flow was from the earlier year, and made this short drift here. And I will now go more or less chronologically with illustrations through this drift with respect to snow. So why do I talk about snow, and what's the role of snow in this expedition? Snow affects more or less the entire radiation balance. It affects the thermal conductivity, the albedo, and also how satellite retrievals, so the depth, the thickness of the sea ice can be measured with remote sensing. But it also affects the nutrient fluxes, the fresh water. So there are many connected properties or processes which are connected to snow. Now, why was this expedition planned? Actually, the planning took more than 10 years. And one of the main reasons is a bit illustrated here in this figure. It shows the temperature change and the potential temperature change at the different latitudes. So here we see the equator, and this arrow shows the uncertainty in the forecasts. And we see that at the equator, it's a quite small one. It's a huge uncertainty for the Arctic. And to reduce this uncertainty, we need more measurements in the Arctic. And that was the main goal of this collaborative project, MOSAiC. It's well known that the Arctic sea ice is in rapid decline, and I will not talk about this. You see that depending on the different scenarios, it may be possible that within 20 years, almost all ice is gone on the Arctic Sea, in the Arctic Ocean. Now, how can we measure this? How can we measure in the Arctic sea ice for an entire year? The idea was that we have a stable platform, the Polarstern, the icebreaker and research vessel Polarstern, and it sits in a more or less stable flow, and then we can measure all these components and processes like radiation, cloud properties, aerosol properties, atmospheric chemistry, sea ice chemistry, seawater chemistry, energy, momentum, humidity fluxes, not only in the atmosphere, also in the sea ice and in the ocean. And then we have all the sea ice dynamics. We have the ocean circulation, and also in the sea ice, in the ocean, the entire ecosystem. And clearly between these spheres, we have also biogeochemical fluxes and also exchange of isotopes. So what we are looking here is this very thin layer called snowpack, and I will go in a bit more detail. So this is the beginning of the expedition, October 4. The first people go out. It's still a little bit light. And now we had to prepare the locations where the measurements take place. As you see, it became dark very soon. As I said, we had, and here in Leg 1 from our team, it was David Wagner, who made many snow pit measurements. And you already see it's not that easy to see the snow in darkness. Now, how does that look, cities in the Arctic Ocean on sea ice? This is a map from midwinter. This map always changed every few weeks because we had a lot of drifting sea ice. And I start here with the Polarstern. So the Polarstern was our safe home and really the base for our measurements. And from this location, from the Polarstern, we had a place where all the logistics was, with the ski-doos, with the piston bullies. And then we had the roads going out to the different places. Here is Med City. Here is Ocean City, which are the largest cities. And then we had different fields, which are not cities, but our stakes. So the snow field 1, snow field 2, snow 1, snow 3, and many of these fields changed, shaped, and disappeared after some time. For example, you see that snow 2 has actually 2 pieces, which was 1 piece, but in end of November, there was a large shear event, and snow 2 drifted, was broken apart. That happened many times. It was a very dynamic environment. Now, how can we measure snow under these conditions and for an entire year? Traditional snow pits where the observer observes grain shape, grain size, and hardness is a bit subjective and also difficult because each observer has a slightly different classification in his mind. So we focused on instruments which are just measuring without any human intervention, or with little human intervention, but with an objective measurement principle. And one of these instruments is the snow micropen. You see it here at work. And it measures the force, here shown force in Newton, and here is the depth. The snowpack was mostly very shallow, and we see here that we have a hard surface layer, usually from wind-blown snow. Then we had something quite weak that was often depth hoar, and then we had another layer which was often very hard. Also, one of the advantages of these instruments is that we can measure really many measurements. We can make really many measurements, so about 1 measurement per minute. Now, how does the snow look like on sea ice? Often when there is fresh ice, it starts with an ice flower. These are kind of a surface hoar, but it's not freshwater surface hoar. It's salty surface hoar. When you take it in your mouth, it's a little bit like chips. So that's one part we will also find later in the snowpack. And then we also found sometimes things we couldn't explain immediately. I will come back to this later. It's an image which we took using our microcomputer tomograph. And when I first saw this image, I was wondering, what's happening here? It's snow, but what happened here? Mid-December was then the first exchange, and David was replaced by Matthias Jacki, Daniela Krampe, and myself. And we measured then from mid-December until beginning of March. Now that's a typical image of our measurement site. Here it's in a rich area where we have a lot of snow accumulation blown here by wind. And you see we have our headlamps. I prefer the white one. Daniela liked the green one. But you see really not that much. You are just focused on the small spot of light where you do all these operations. An important part was the micro-CT, so micro-computed tomography. And with this instrument, which was given to us by Scanco, we could, and was in the AVI cold container at -15 degrees C, we could measure snow samples with 80 millimeter diameter with a resolution of 28 micrometer. So really a very high resolution, and we could transport these samples from the field in these containers directly in the code lab and measure them with this instrument. And I come back to the question, what is this? These darker particles, it's a wind-blown snow. It's a buried surface of ripples, small, you can say microdunes. And between these ripples, we have fresh snow. So this, you see these edgy particles, this is fresh snow. And this formed then this complex mixture between surface wind, or between wind transported snow, so very fine, very small particles here at the edge, very densely packed, and very loose new snow. So from these many slices, we get from the computer tomograph, here, for example, depth hoar, we see the nice scrolls that are formed in this depth hoar on sea ice. We can then digitally create 3D structures. And I show here an example. You see the scale, this scale is here 1 millimeter. And what we see here at the surface is a hexagonal column, so a new snow crystal. It has at the top and the bottom, it has a plate crystal. As we see also here, we have also this hexagonal crystal, and here we have a dendrite. And so we see from this tomography, which was made from new snow, that in this snowfall we had many different kind of different snow types. Again, here you see this hexagonal column, and at the top and bottom, the flat plate. So with this instrument, we can really go into the details of the snowpack. We can not only see the snowpack, we can also see the interface between the sea ice, so what I show here with the pointer is the interface between the solid ice and above the snowpack. And you may, it may be a bit difficult to see, but these quite large structures are depth-hoar structures, so strongly metamorphosed snow. And in this metamorphosed snow, we have these reddish things, and this reddish material is has a very high X-ray contrast. And we guess now that this is actually a mineral, a crystal, ichite, which is formed on sea ice or in this type of sea ice at this temperature. And interestingly, we find these crystals not only in the sea ice, but also in the snowpack, or a few millimeters into the snowpack. Now, what do we do with these images? Here it's an example of a quite typical winter snowpack. At the surface, we have very small particles, connected, sintered snow crystals. They are wind transported, and then we soon get these large structures which are more or less vertically oriented, which is depth-hoar. And now we can measure the density and the specific surface area of these particles or this structure. And that's shown here in this figure. We have in magenta the density, and the density changes is at the bottom around 300 kilogram, goes down to 150 in this very loose part, increases again, and is again quite low at the top. The specific surface area gives us an idea about the surface per ice volume. So how fine, how large is the surface? And this is a very important parameter to describe metamorphic processes and also for chemical processes. And we see at the surface, we have a high specific surface area, which is then much lower in this metamorphosed snowpack. The surface area can be converted to an equivalent optical diameter, which is a very small here in these small particles, and then gets much larger up to 300 micrometer at the bottom. Now, in winter, there is no light, so there is no albedo, or we can't see there. When there is no light, the albedo has no effect. But in summer or in spring, when the light comes up again, that will be very important. As I said, it's difficult to see the snowpack when you have just a very limited view. So we used also near-infrared photography. This black hole here is the lens of the camera, and then we had LED lamps which produced near-infrared light because it's pitch dark. And when you take a picture of people sitting here in front, it looks like this. But the interesting thing with this box is we can document the two-dimensional stratigraphy. So on the left, we see a raw image, and we already see that one layer is much darker than other layers. When we enhance a bit this image, we can see that even better. We also see that there is a structure which is crossing the entire picture. That's probably our old dune feature here. These are very strong depth hoar layers, these dark features. And when we do a bit more processing, we can also calculate the specific surface area of these different grayscales. So we have a two-dimensional measurement of the specific surface area and the stratigraphic layers. In the beginning of March, so actually the handover was the 3rd of March, 2020. Our Snow team was replaced by Amy McFarlane and Steffi Arndt here in action. And you already see it now becomes light. The sun is slowly coming up. But not only the snow, it's still very windy. And actually spring is, the spring months, so March and April are the coldest months in the Arctic, in the high Arctic. But then it becomes slowly warmer in May, and actually the snow starts to melt and we get a completely different snow. And this, we call it summer snow, or a bit more technically, surface scattering layer. And also from this surface scattering layer, we could now take computer tomographies. Here you see the very top of this layer. It has very sharp fins, and the sharp fins cause that we have actually at the very surface a high specific surface area and quite a very small optical diameter. So this top layer affects the albedo very strongly. And then we have an increase over this few of these tens of millimeters, an increase in the optical diameter, as we see from this larger picture, which has the same height as here, so 70 millimeters. And we see again this still strongly vertically oriented structures from the past snowpack. Now, what can we do with the Snow micropen? As I said before, it's an instrument which just measures without human classification. And we can also observe very nicely changes over time. When we measure always at the same locations, we can actually follow the different layers and then build almost three-dimensional stratigraphy. We did not only these more technical measurements or more instrumental measurements, we also used very common and older tools like a density cutter. And we see that when we just map this, all these measurements, here on the x-axis density and the y-axis snow height, we see that different lakes have a different pattern. So in Lake 1, it's the pattern here. So we had the density between 200 and 400 with increasing density, the higher the sample was taken. In Lake 2, it was, this was Lake 1, so very high density. And Lake 2, we had a larger variation, especially we had here a lot of lower density values, probably from the depth hoar. And in the other lakes, we had, again, a shallower snowpack with a high variability of density. These are all very preliminary results. We are still in the mid of evaluations. And now we can also classify these different measurements according to our snow micropen measurements. Okay, now I was completely confused, sorry. The picture here is from Lake 1 and 2, and here we have actually in the colors different classifications. So here are melt forms, here are wind-packed and rounded grains, here are the precipitation particles, and in this box here is depth hoar. So we try also to classify our measurements according to the traditional grain shapes. Lake 4, as you see, now the environment changed dramatically. There are melt ponds and there is only very little kind of this summer snow left. Amy McFarlane made a nice graphical illustration what's going on. Fortunately, nobody flew up with the balloons, but you can imagine there were a lot of activities from the atmospheric people, from the ocean people, from the eco group, measuring all the different processes. The snow was not really snow, it was all this surface scattering layer. Here again, a CT. Now there is not much depth of this layer in this image here, and the grains became very, not anymore very snow-like. It's melted forms, very large melt forms. We can also observe the structure using near-infrared photography, so we get a good quantitative description of this surface. And more artistically, it looks like that, like this beautiful image of the surface scattering layer with these nice boundaries between probably the sea ice crystals. Again, it becomes darker. Now the Polarstern moved back to almost close to the North Pole because it drifted out of the sea ice. And here Ruschle took over, here with the snow micropen. And she had on this sled all the instruments I just explained before. The snowpack was still very shallow, and the melt pond started to freeze. We see also it's not a completely flat surface. we have already some ridges. Now, the freezing ice on the ponds has bubbles, here nicely shown in this CT image. It looks like that the pond freezing and the lead freezing are slightly different, create different bubbles. Here it's not the ice, it's the pores in the ice. But also the snowpack started to build up. And that was very nice that in Lake 5, we could actually see the real beginning of the snowpack, of the new winter snowpack, which we missed in Lake 1 because the Polarstern arrived already on a surface which was already snowed in. And here in the morning, it was new snow. So we see here these small particles at the surface of the old surface scattering layer. And during the day, these new snow then melted and formed these larger snow structures. There was a huge dynamic. We had new snow on the surface hoar, even larger surface hoar formations. So the snowpack already in September starts to form anew and with many different snow forms. So what did we get? We get many snow pits. What's shown here is the start in October and the end in October 2020. A horizontal line is that we could make a continuous series of snow pits at one location. And you see that all locations, depending on the drift events, sometimes these snow pits could only, or maybe 1 or 2 months, and then we had to go to a new place. So where are we? We sampled over almost 600 snow pits. We measured almost 7,000 snow micropen profiles, and we could scan 600 micro CT scans, each about 10 centimeter. So we could scan almost 60 meters of snow. So we have really, we could document the snowpack during this drift in a very detailed manner with new instruments which give much more information than a traditional snow profile. And we are now working on evaluating all this data, this exciting data. So that was my end, and I'm looking forward to your questions. Thank you for your attention.
Perfect. Thank you for that, Martin. Do we have any questions? Please indicate any questions in the chat, and then you can just unmute yourself or type the question in the chat if you do not have a microphone. There is a question from Roger. Roger, do you just want to unmute yourself?
Yeah, I will do, but Paco Navarro was just before me in the chat with a question. I don't want to jump the queue.
Oh no, just go ahead, and Paco can go next.
Oh, okay, thanks. Thank you very much, Martin, enjoyed that. Did you do any shallow geophysics while you were out there? For example, a very high frequency GPR alongside the Snow micropen. It's been very interesting to compare the what I would call cone penetration testing results and the micropen results to GPR.
We did during leg 2, I did a few GPR, high frequency GPR transects, but the antenna broke down then because it was too cold, and it remained dead for the rest of the expedition. But there are a few, or about 500 meters of GPR transects at 2 time steps.
That's great. Thanks very much. That's rotten luck, but yeah, thanks for the answer.
Perfect. Paco, do you want to go next?
Yeah. Hi, Martin. Nice to meet you again. It was wonderful experience and huge amount of data. I have a question which is just more curiosity about the weather conditions and about how often you could actually work so on average, or maybe during the nighttime or during the daytime, how often could you actually work in the field because of weather conditions?
Yeah, we could work we could do the snow pits every week. So, but we went out also under quite bad conditions. But because our instruments were quite robust and we didn't have to make this traditional snow pit stratigraphy, it was also possible to work in windy conditions.
Okay, but then if you try to go out, how often you couldn't because of the strong wind, for instance?
It was
just when you were there. You were there from I think December to mid-January, you said?
Yeah, from mid-December to end of February. So
end of February. Okay.
March of 3.
So during this time, how many times you tried to get out, but you couldn't really because it was too windy or too?
It was 2 or 3 days.
Just that. Okay. Yeah. That's good. Okay. Thank you.
Come.
There's also a question by Doug. I'm not sure if you want to ask that yourself, Doug. We can't hear you. I think you're unmuted.
Martin? Okay.
No.
Hey, they were unmuted. Excellent talk. Really incredible adventure that you and your colleagues have been on to do this incredible expedition to the Arctic. And I am, of course, very interested in the computer tomography that you've done. And my question is, have you developed a sense of how frequently in time a computer tomography of the snow in the Arctic needs to be taken in order to see how the snow is changing?
That's a challenge. Or we took in every snow pit samples. And at the moment, I have to say, each sample looks slightly different. And we could process 3 samples, about 2 to 3 samples per day, so 20 to 30 centimeters per day. And we ran 7 days, almost 7 days a week. So we could take quite, as I said, many samples. And there is so much spatial variability that I think it's really good that we could take so many samples, because also when you look at the snow micropen profiles, there is good spatial correlation about for 1 meter, but then it breaks down.
Thank you, Martin. A really wonderful talk and great wishes and kudos to your group for such a marvelous expedition. Thank you.
Thank you.
Great, thank you. There's also a question on Facebook by Adam Cashton. And I think it's a question, and he asks if you can apply this penetrometer for ice shelves, so 60 to 100 meters thickness, or only for sea ice and snowpack, or 15 to 20 meter for dynamic sea ice.
Yeah, the snow micropen measures not deeper than 1.5 meters. So it's really for a shallow or for snow. It's not for ice and not for fern.
Is that only because it's limited to the depth, but let's assume there wouldn't be any snow? Could you then penetrate into ice, or is it too stiff?
Ice is too hard. It doesn't penetrate ice.
Okay. Perfect. There is a question by Nick. If you're here and happy to unmute yourself, go ahead.
Hi, Martin. Thank you very much for your talk. I've got 2 quick questions about the micro CT. They're quite sort of technical, but of interest to me. Firstly, did you need to cast the samples? And if so, did you use the new contrast enhanced technique that Michael published recently in Journal of Glaciology?
The snow was so hard that we didn't have to cast the snow. And we had quite a special technique, and because our instrument was so close to the sampling site, it was also possible to transport with a lot of care, like eggs, to the freezer container. So luckily we didn't have to cast, because the technique Michael just published was not 100% ready.
Okay, that was, well, both fortunate but also great. It may answer my second question as well, which was how hard did you find to not cast but take samples from those weak depth hole layers?
Yeah, this weak depth hole, so the depth hole was actually not that weak, and because we could sample with 80 millimeter diameter, with a lot of care, it was possible to use this depth hole to extract this depth hole layer without that they collapsed.
That's great, Martin. Thanks very much. It's an incredible data set. Thanks for your presentation.
Thank you.
Okay, there is another question by Mareike Wiese, which is about how the snow structure evolved at the snow-sea ice interface.
Yeah, Mareike was my former PhD student, and she looked at ice-snow interfaces, and I have to say it evolves exactly as in her not yet published PhD thesis.
Okay. Are there any more questions? Let me know in case I've missed any in the chat. There are lots of like clapping hands in the chat and thank yous for you, Martin.
Thank you.
Okay. I think if there are no more questions and no more questions on Facebook, do you have that last slide to announce next week's talk?
Yes. So next week, Hilmar Gudmundsen will talk about dynamics of large ice masses at the same time. And I'm sure it will be interesting again to know more about Antarctica, as I see from the picture.
Okay, great. If there are no more questions, then I think let's close down the meeting and see you all next week.
Thank you,
Thank you,
Rebecca.
Martin.
Bye, Martin.
Bye.